Welcome to EMR Physics. I am Raju, NCERT 12th Physics. We are solving the numerical problems given in Chapter 5, Magnetism and Matter. In this video, we are going to see how to solve the book bag problem 5.5. The problem is a bar magnet of magnetic moment 1.5 Joule per Tesla lies aligned with the direction of a uniform magnetic field of 0.22 Tesla. Subdivision A. What is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment? Number 1, normal to the field direction. Number 2, opposite to the field direction. Subdivision B. What is the torque on the magnet in cases 1 and 2? This is a given problem. Let us see what are the numerical data given in this problem. Magnetic moment of the bar magnet is given, which is 1.5 Joule per Tesla. Magnetic field is given, which is 0.22 Tesla. What is asked? There are two subdivisions. In the first subdivision, we have to find the amount of work required by the torque in two cases. In the first case, we have to find the work required by the torque to turn the magnet normal to the field, and in the second case, we have to find the work required by the torque to turn the magnet opposite to the field direction. In the second subdivision, we have to find the torque on the magnet in these two cases. Let us see how to solve this problem. The numerical data given in this problem is magnetic moment M is equal to 1.5 Joule per Tesla. Magnetic field B is equal to 0.22 Tesla. What is asked? We have to find the work required by the torque in two cases. In the first case, to turn the magnet normal to B, and in the second case, to turn the magnet opposite to B. Now let us see the first case. Case 1, to turn the magnet normal to B. This is the direction of the magnetic field. Initially, the bar magnet is in the same direction. If the bar magnet is in the direction of B, the magnetic moment will also be in the direction of B. This is the direction of magnetic moment. Since the bar magnet is in the direction of B, magnetic moment is also in the same direction. Magnetic moment M and magnetic field B are in same direction. This is the initial position. This is position 1. The angle between M and B is, the angle is theta 1. Theta 1 is equal to 0 degree. Since M and B are in the same direction, the angle between M and B is equal to 0 degree. The potential energy in this position is U1. This is the direction of the field. Because of the external torque, the magnet is turned normal to the field. If the magnet is normal to the field, magnetic moment is also normal to B. So M and B are normal to each other. M and B are normal. This is position 2. The angle in this position is theta 2. Since they are normal, theta 2 is equal to 90 degree. The potential energy in this position is U2. So what is asked? We have to find the work required by the torque to turn the magnet normal to B. The amount of work is calculated by finding the difference between the potential energy. So the amount of work required can be calculated by finding the potential energy difference between these two positions. So work required is equal to U2 minus U1. U2 is the potential energy in the second position. U1 is the potential energy in the first position. The difference in the potential energy is the work required by the torque. U is the magnetic potential energy. The magnetic potential energy is given by U is equal to minus MB cos theta. Therefore, we can write U1 is equal to minus MB cos theta 1 and U2 is equal to minus MB cos theta 2. Therefore, the work required W is equal to u2 is minus mb cos theta 2 minus mb cos theta 2, and here we are having minus what is u1? u1 is minus mb cos theta 1 minus mb cos theta 1. So this is equal to minus mb cos theta 2 minus of minus plus mb cos theta 1. We know the value of theta 1, theta 2, m and b. Therefore, this is equal to minus 1.5 into b is 0.22 into cos, what is theta 2? Theta 2 is 90 degree. M and b are normal to each other, plus m is 1.5, b is 0.22 into cos theta 1 is equal to 0 degree. Cos 90 is equal to 0. Cos 0 is equal to 1. Therefore, this is equal to, this will become 0, and this is 1.5 into 0.22. If we calculate, this is equal to 0.33. So this is W. W is the work required by the torque. Unit of work is joule. So this is the work required by the torque to turn the bar magnet normal to the magnetic field. Now let us find what is the work required by the torque to turn the bar magnet opposite to the magnetic field. Now let us see how to calculate the work required by the torque to turn the magnet opposite to B. Let this is the direction of the magnetic field. Initially the bar magnet is in the same direction. Therefore, the magnetic moment and B are in the same direction. This is the initial position. In this position, let the angle is theta 1. Since M and B are in the same direction, theta 1 is equal to 0 degree. The potential energy in this position is U1. Because of the external torque, the magnet is turned in such a way that the magnetic moment is opposite to the direction of the field. So the external torque turns the magnet in such a way that the magnetic moment is opposite to B. M and B are opposite to each other. Since M and B are opposite, angle theta 2 is equal to 180 degree. Angle in this position is theta 2 and it is equal to 180 degree. The potential energy in this position is U2. We have to calculate the work required by the torque to turn the magnet in such a way that magnetic moment and B are opposite. Work required is equal to difference in the potential energy, that is U2 minus U1. The potential energy difference is the work required by the torque. This is equal to, we know U2 is minus mb cos theta 2 minus U1 is minus mb cos theta 1. This is equal to minus mb cos theta 2 minus of minus plus mb cos theta 1. We know the value of theta 1, theta 2, m and b. Therefore, this is equal to minus 1.5, this is m, b is 0.22 into cos theta 2 is 180 degree plus m is 1.5 into b is 0.22 into cos theta 1 is 0 degree. Cos 180 is minus 1. Cos 0 is 1. Therefore, this is equal to minus 1.5 into 0.22 into minus 1 plus 1.5 into 0.22 into 1. This is equal to minus of minus plus. Therefore, 1.5 into 0.22 plus 1.5 into 0.22. This is equal to 0.66. Therefore, the work required W is equal to 0.66. Unit of work is joule. So, this is the work required by the torque to turn the bar magnet opposite to the direction of the magnetic field. So, this is the answer for the first subdivision. Now, let us find the answer for the second subdivision. In the second subdivision, we have to find the torque on the magnet in two cases. In the first case, M is normal to B, and in the second case, M is opposite to B. Here, M is the magnetic moment. Now, let us find the answer in case 1. In the first case, M is normal to B. Since M is normal to B, the angle theta is equal to 90 degree. We can find the torque by using the relation torque tau is equal to mb sin theta. This is the magnitude of the torque. We know the value of m, b and theta. M is 1.5, b is 0.22 into sin angle is 90 degree. Sin 90 is 1. Therefore, this is equal to 1.5 into 0.22 and this is 0.33. This is the torque on the magnet when the magnetic moment is normal to B. Unit of torque is Newton meter. Now let us find the torque in the second case, case 2. In the second case, M is opposite to B. Therefore, theta is equal to 180 degree. Hence, torque tau is equal to M is 1.5, B is 0.22 into sin 180 degree. We are using the same formula. M is 1.5, B is 0.22 into sin angle is 180 degree. Since M and B are opposite to each other, sin 180 is equal to 0. Therefore, 0 into anything is 0. Torque is equal to 0. So, this is the answer for the second subdivision. In the first subdivision, we have calculated the work done, and in the second subdivision, we have calculated the torque. This is the answer for the given problem. If you find this video is useful, please subscribe the channel, share it to your friends. If you have any doubts, comment below. Thank you for watching this video.